doing well. We're going to look at searching and sorting algorithms today. So I'm going to jump straight in and show you how these work. In total, we have got 5 to worry about: 2 searching algorithms and 3 sorting algorithms. It's quite a lot, but actually, do you know, they work in a very, very simple way. So let's, without any further ado, jump in and see what they're all about. Let's start off, first of all, with making sure we understand what searching and sorting is. Searching for an item means you've got a list, which is called an array. So when I use the word array, it's a list of items. So, for example, dog food, cat food, bananas, and tomatoes. A strange shopping list, but it's a list. It's an array, okay? It's a certain number of items, usually separated by commas when it comes to writing it in pseudocode or in a high-level language. So searching and sorting is something that's used by thousands of applications, and we're going to look at 5 different ways that you can achieve these goals. We're going to start by looking at 2 ways that you can search, and those are using a linear and a binary search. Let's start with a linear search. It's really easy. Let me just sensitize you to this little grid which we have here. So the first thing is the numbers in our list, in our array, are 10, 6, 3, 5, 54, 9, 23, 8, 2, right? That's the array that we're going to search through, and we're looking for number 5. Now you say, well, hang on, number 5's there. This is quite easy. Yes, it's quite easy to do it once with a list that small. But if you've got a list of tens or hundreds of thousands of things, this is where computers come in really, really handy. All right. Now, the next thing to point out to you is that we've also got this index that might be confusing you. This index here means whereabouts in the array list does this fall. So, for example, and it starts at 0 rather than starting at 1. So this is search item 0, this is search item 1, search item 2, 3, 4, 5. Sorry, list item 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So in other words, this one is at index 4, 54 is at index 4, 3 is at index 2. I hope that makes sense. Right. How does a linear search work? Really straightforward. It starts at index 0 and it looks at the number which is in index 0. And we're looking for 5, don't forget. Is 10 5? No. So guess what? We go to the next one. Is 6 5? No, it's not. And as you already know, 3 isn't 5 neither. But look, 5 is 5. So it's simply, and then it returns the search item, okay? So the algorithm stops once 5 is found. So you simply go to the first item in the array, and then you go through the array one by one until either you find the item or the item's not found, in which case it'll return not found. All right? So you increment the index by 1, and then you keep going until you found the item. Really straightforward, isn't it? So if only everything was as simple as a linear search. I'm not going to focus on the pseudocode today. I'm going to jump straight in and look at your binary search. Now, in addition to being able to perform these searches and sorts on the data they give you, you also need to understand what the benefits and drawbacks of the different searches and sorts are, okay? So the binary search, the one we're going to look at now, is much more efficient than the linear search that we looked at a minute ago. But can you think about why this particular searching method is inefficient? So say, for example, your item, the item you're looking for, the search item, is at the very end of your array here, and you've got an array, a list of 10,000 items. It's got to search 9,999 items before finding yours. So it's a very simple bit of code to write, but it's not very efficient, okay? And it can take a long time. So that is your linear search. So let's jump and look at the binary search. So the idea behind the binary search is that you look at your array and you find the middle item in your list. And then you look at the middle item and you say, and you ask the question, and I'm now here, you ask the question, is that middle item, and we found the middle item, is that the one we're looking for? Either yes or no. If it is the item looking for, well, happy days. You can return the item, search item found. If it's not, you consider the item that you're looking for, and you ask the question, the item I'm looking for, is it bigger or smaller than the middle item? All right? And then depending upon the answer, you will then delete half the list. You'll simply ignore it, all right? And you'll keep going with that process. So just to sort of put a bit more information on that for you, let's look at how this actually operates. Again, let me just sensitize you to this here. These are the numbers in our array, and I'm going to use array for list all the way through now. These are the numbers in our array, and this is the index. So this is item 0, item 1, item 2, item 3, and 4. Okay, right? So here's the thing. We are looking for number 3 in this list here, which unhelpfully is 1, 2, 3, 4, 5, 6, 7, 8, 9. But there we are. It's a sorted list, okay? And that's another important thing, is that binary searches require the list to be sorted. Often a question they ask you at GCSE. So we're looking for item number 3. So the first question is, we're looking for number 3. We're looking for this guy here. So we go to our list and we find the middle item. You might be asking, well, how do you work out what the middle item is? Well, you add all of these together and you divide by 2. How many indexes have you got? We've got 9, so we're at here, okay? So we have identified this as being our middle item, all right? And the question is, we're looking for the number 3. And the number we found in the middle place, in the middle position, is 5. Is 5 bigger or smaller than 3? Well, 5 is bigger than 3, which means that everything this side of 5, we know it's not going to be in there because this list is sorted. So therefore, we only now need to focus on this. We can ignore the right-hand side of the list. Easy peasy. Right, next thing. This is the left-hand side of the list. We find the middle item. Now, because this is 4, there are 4 elements here, there isn't really a middle item. So you go to the middle and then you move up 1. Okay, so that's why we have gone for index 2 as our middle item, because we've taken the low and the high and we divided it by 2. There's the low item. So 0 to 3 divide by 2, and this is our middle item. So is that the number we're looking for? Yes, it is. Look, it's a 3. Happy days, we found it. However, if that wasn't the item, you would do exactly the same thing again. Is the search item, the item we're looking for, bigger or smaller than the middle number? If it's bigger, if it's smaller, do that. Okay, so that is how that works. That is your binary search. I'm not going to show the pseudocode because if you are aiming for a 7, an 8 or a 9, spend 5 minutes going through this to make sure you actually understand how this works. It will help you hugely, A, in your programming, B, in understanding searches, and just generally in terms of how you might go about programming it, okay? Give you some ideas. But I'm not going to go through that now. Now I'm going to look at the sorting algorithms, and we have got the bubble sort first of all. The bubble sort works this way. It's very simple, and it works through a list by making comparisons between pairs. So let's look at this one here, and don't forget we're looking to sort this. So we're looking at this list here, 3, 2, 4, 1, 5, and we want to turn this list into a sorted list, all right? Now, the bubble sort is an inefficient algorithm, but it's very simple. And it's inefficient because it has to perform multiple passes. It's got to go through the data, through the list, the array, several times, at least twice, often more times than that. So let's look at how this works. So from our list, we look at the first 2 items, 3 and 2. The question is 2 less than 3, or is 3 bigger than 2? Well, yes, we need to swap these 2, don't we? So that swap takes place, and it becomes 2, 3. Then it compares 3 and 4. Do those need to be swapped? No, because 4 is bigger than 3, so it's in the right place. We then compare 4 and 1. Do we need to make a swap? Yes, we do, because the 1 is smaller than the 4. So we make that swap. And then lastly, so we've now got 2, 3, 1, 4, and then we compare the 4 and the 5. Do those need swapping? No, because they are already sorted. So that is the first pass. We've passed through the data once, and we've made a couple of swaps too, I think. All right. But you can see the problem is you've got to go back and do this again because the list after our first pass, is it sorted? 2, 3, 1, 4, 5. No, it's not, because that 1, it's all sorted apart from that 1, which shouldn't be there. The 1 is supposed to be over here. Okay, so the 1 is supposed to be, come here, arrow. The 1 is supposed to be over here. All right, that's where it needs to be, over there. So we need to complete another pass of the data. So a bit like Groundhog Day, we go and do exactly the same thing again. So we look at it again. 2 and 3, do we need to swap? Nope. 3 and 1, do we need to swap? Yes. Can you see now why it's called a bubble sort? Because this 1 is gradually bubbling its way towards the left-hand side of the list. That's why it's called a bubble sort. It doesn't involve bubbles at all. So we make that swap, and then we go through the rest of the list, but we know it's all sorted, so it won't make any more changes. And then guess what? We have to go through it again. Because now we look at the 2 and the 1. Do we have to swap? Yes. So the 1 is now in the right place here. And we know that 2 and 3, 4 and 5, they're fine. It'll go through it. It goes through every single pair and compares them. Now, at this point, the third pass is complete and our data is sorted. But the problem is that the algorithm, and this is a bit of a sort of clumsy way of saying it, the algorithm only knows that it's sorted when it's been through the whole list and not made any changes. So it's been through the list and it's made a change, but it will have to go through the list for a last final time, and when it makes no changes, if it goes through the entire list and compares all the pairs and nothing has been swapped, then the algorithm is complete, okay? And that's how you end up with your final list of 1, 2, 3, 4, 5. And you're thinking, I could have done that in 10 seconds without a computer. But like I said, if we end up with hundreds, tens, millions of bits of data, computers do it much more quickly than we can, okay? So that is how that works. All right. This is the pseudocode. Again, those of you aiming for the 7s, 8s, 9s, I would urge you to have a look and see what this temp value is doing here. I would also urge you to have a look at the flag that they've used with a while, and the end while is down here. So the flag for when it's sorted, which will then ping you out of the algorithm down here, okay, at return sorted list. All right, so that is our bubble sort absolutely done and dusted. I'm now going to push on and have a look at the insertion sort. It's quite similar in many ways to the bubble sort, but the bubble sort works by finding the next largest or smallest element. The insertion sort works slightly differently. It takes the element, so it takes the left-hand side element in the list, the first item, and it puts it in a sorted list of 1, and then it relates the rest of the items to that list. So if you've got 50 items in a list, it looks at the first item and goes, right, I'm going to treat you as a list of 1 item, and that list is sorted because it's got 1 item in it. I'm then going to add the other items into it in the right place, which is basically how it works, okay? So the way that it tends to work, and let me try and show this to you on here, that's perfect. All right, so if we look at the first item there, we've got search items 85, 12, 59, 45, 72, 51, all right? So we're going to use the insertion sort to make sure that this list is sorted. So what you do over here, and let's pick it up here, you look at the 85, and we're going to assume the 85 is a list. It's then treated as though it is in a sorted list of 1. And then it looks at the next item. It looks at the 12. And it asks the question, where is the 12 in relation to the 85? Well, 12 is smaller, so it shifts the 85. Ooh, good chance to use an arrow here. It shifts the 85 1 space to the right, okay? One unit to the right. And it pops the 12 in like so. All right? and then it just keeps going in the same way. So the next thing it'll do, so we've now gone from 85, 12, 59 to 12, 85, 59, and then it looks at the 59, and it compares it to the 85. Well, is it bigger or smaller? It's smaller, so it should definitely be here. But also, it then looks at the 12, and the 12 is less than 59, so it doesn't need to go across to here, okay? It can just sit there. Then we look at the 45. The 45 we know is smaller. Can you see how it's always referring it back to the 85? And then it works its way down the rest of what is a sorted list, okay? So this list on the left-hand side is always sorted, and it starts with one item, and it obviously the number of items grow. So 45 is less than 85, so it needs to go here. It then compares it to the next item, which is 59. 45 less than 59, so it ends up plonking it here. Well, it doesn't plonk it, that's not a very computer sciencey way of putting it, but it places it there, okay? And if you look at this, it works in exactly the same way all the way through. And my advice to you is that, because listening to someone explaining an algorithm like this it's quite hard to understand. But once you understand the basics of it, it's then just a question of looking through the algorithm to see how it works. But that's the idea, is that it takes the left-hand item, the first item in your array, and it treats that as a sorted list. And it looks at the next item and says bigger or smaller, and it puts it left or right of that item. It looks at the next item, and then again, it works out where to put it. So it takes each item and it puts it into the right place, okay? So that is how that's how it works. So it compares the second value in the list with the first value, and if the second value is smaller than the second value is moved left until the value on the left is smaller, and it just keeps going in that way, okay? So that is your insertion sort. Merge sort. Merge sort is nice and simple. Right, let me talk you through this. So a merge sort works in this way. So if we start up here, and it's just easier if I talk about the list in front of us here. So let's start here. This is our unsorted list here, okay? 2, 45, 6, 9. And we want to get down to this one here, which is our sorted list. So the very first thing that it does is that it splits all of the items into individual items. So if you were showing this on a page, you would take this particular array here, this list here, and you would simply redraw out these boxes, except move them ever so slightly apart. So you've got a little space between 2 and 45, a little space between 6 and 9, and so on and so on. So you're showing that the items have been split into separate entities, okay? That's the very first thing that you have to do. So they're split apart, okay? And then you start off by putting it into, so you can see here, right? Let's just run through this as we go. Right, so first of all, this list is split apart, okay? And it's split apart, first of all, into 4s, then it's split apart into 2s, and then it's split apart into individual items. They haven't shown this very well. There should be sort of equal spaces there between these, okay? And then how does the sort actually work? So it takes the first two items, which are 2 and 45, and it sorts them as a pair. So that stays the same because 2 and 45 is sorted. It then looks at 6 and 9, and it sorts those as a pair. Well, guess what? 6 and 9 is already sorted. It then looks at 15, 12. Well, 15 and 12 isn't sorted because 12 is smaller than 15. So it sorts them into a sorted pair, which rather than being 15, 12 is now 12, 15. 7 and 8, it leaves it as it is. So it sorts it into pairs, it sorts it into sorted pairs, and then it sorts it into sorted 4s. So it takes these two here, it takes these two items here, this one and this one, and it brings them into this 4 here. So it takes 2, 45, 6, 9, which we know is going to be 2, 6, 9, 45, and then it goes to this side, and it takes these 4 here, and that becomes 7, 8, 12, and 15. And then finally, it puts it into a sorted list of 8 down here, okay? So that's how that works. So when you're asked this question in the exam, the idea is you split your array out into individual items, and to be honest with you, they don't really expect you to cover this part here. All you've got to do is say that the list is split into individual items. See, you rarely have to explain that into individual lists, but the first job you will do is show that they are individual items, individual lists. So this is now 8 arrays, okay? So you're turning 8 arrays into a sorted array of 2, a sorted array of 2, a sorted array of 2, and a sorted array of 2. You're then taking these and you're turning this sorted array of 2 into a sorted array of 4, okay? Like so. So these become the 4, these become a 4, like so. Come on, cursor. And then these guys become an 8 afterwards. All right, so that is how your merge sort works. It's actually quite simple. Ladies and gentlemen, searching and sorting. I will send Mr. Vallely Godfrey the list that will tell you the advantages and disadvantages of each, and please use that as part of your revision schedule. I will see you the same time next week, and do try and put in some revision between now and then. See you guys. Bye-bye.